Okay, welcome to this week's lectures. I left you last time thinking about this fantastic image, first image of the sort of shadow of a supermassive black hole in the center of another galaxy. You recall that we saw that all galaxies have these supermassive black holes in their center. I was asking you to work out the angular size of this particular black hole, so the one that's had its first image taken. So you need to work out the physical size. I gave you the mass. So this is the Schwarzschild radius, the radius of the event horizon. So you just need to put the mass in here. So that was just over 9 billion solar masses. Okay, and that gives you a size of 2.8 10 to the 13 meters. Apologies, that formula shouldn't be there, but forget that. So that's about the size of the solar system. Okay, so that's around about 100 AU, a couple of hundred AU, something like that. So that's the size, in a sense, of these supermassive black holes. So you've got 9 billion solar masses all crammed into the size of the solar system. So this is all pretty extreme stuff. And then you can work out the angular size as usual, just L over D in radians, but then scale up by this factor to give you arc seconds. So that gives you 10 to the minus 5 arc seconds, or 10 micro arc seconds. Okay. So that's the radius. So the sort of diameter of this thing is about 20 micro arc seconds. The shadow effect here is a bit larger than that. So like sort of 30, 40 micro arc seconds. But this, you know, as I said, this is the highest angular resolution image ever made. It's made by a global array of telescopes working at 1 millimeter. So go and have a look at the Event Horizon Telescope web pages on the Learning Resources page, and yeah, you can, and of course you can work that out for yourself from what we learned in workshop 1. Right. Okay, so we're on the final part of the course now. Another new backdrop. So we're looking sort of much further out into the universe now. So we're going to look at the distribution of sort of galaxies in the universe. And so the first step on that road is, how do we work out the distances to galaxies? Okay, obviously we looked at the distances to stars at the beginning of the module with the trigonometric parallax method, which is, you know, these days with the Gaia satellite, good for getting distances to stars within our galaxy, but how do you find the distances to other galaxies? So we're going to go and discuss mainly this method, well, only this method, the standard candle method, and 2 different types of sources that are used for that. So what do we mean by a standard candle? Sort of slightly strange term, but when you think about it, it's okay. So basically we want to be able to know the intrinsic brightness of an object, so that when we measure its apparent brightness, we can use, you know, we can then find the distance that way. So basically we need to know the absolute magnitude of an object beforehand, independently of its distance. Okay. So that's what the term standard candle means. Standard meaning, you know, it's a kind of gold standard. We know how bright it really is, and candle as in brightness. Okay. As we've learned in recent lectures, then the effect of interstellar dust along the line of sight will change the apparent magnitude and make us think the object is further away if we don't know what this value is. So we definitely, if we want to do this accurately, then we need to know what the total visual extinction is as well, before we can use this method. And of course, what we're using is this equation, which hopefully is familiar to you now. Okay, so the sort of distance equation relating apparent magnitude, little m, absolute magnitude, which is what we're going to get somehow independently for our standard candles sources. We'll need some way of finding AV as well, and then we can solve this equation for D. So we would work out the distance to galaxies that way. So what are we looking for in one of these standard candle sources? Well, it would be useful if it was bright, of course, because the brighter an object is, the further away we can actually detect it, and therefore we can measure distances to more distant objects if our standard candle is some kind of intrinsically bright source. We need to be able to, work out what kind of source we're looking at. Okay, so when you look at a galaxy, you've got 100 billion stars in there. So whatever type of object we're going to choose, we need to be able to recognize it so that we can pick them out and use them. And the key thing, of course, is it's going to need to be accurately calibrated in terms of knowing this absolute magnitude. So that means that we can't really use normal stars. Okay. For a start, if you wanted to get the absolute magnitude for a normal star, like a main sequence star or supergiant star, something that is quite bright, you'd have to get a spectrum, but getting a spectrum requires a lot of light because you're going to spread it all out in order to get the spectral type. So that would limit the method in any case. And I've tried to impress on you before that that method of spectral typing to get to the absolute magnitude is not actually that accurate. You could easily be half a magnitude or even a magnitude out, which basically isn't very accurate, as I think we proved to ourselves before. So so we need to look for some other kind of object where we could get a better calibration of the absolute magnitude. And this might sound incredibly counterintuitive, and it is. But basically, there are certain types of variable star that turn out to be extremely good for this purpose. Now, we haven't talked about variable stars in this module, and I'm not, apart from this, we're not really going to. If you want to read around the background of that, you can, but it's, it's not part of this module. There's lots of different types of variable star out there. So by variable star, I mean a star that changes in brightness with time. Okay, and so there are, like I say, there are lots of different types of objects that do that. So various types of evolved star, as they evolve through certain stages of their evolution, they become somewhat unstable and start to usually sort of pulsate in a regular fashion, and that causes their brightness to change with time. So that's what we mean by a variable star. So we're only going to look at one type of these, and these are the so-called cepheid variables. Okay, so they're a sort of famous class of variable star. So the cepheid variables are named after delta Cephei, which was the original sort of prototype in this class of variable star. So they are definitely in this category of stars that become unstable during their evolution, okay, and they basically pulsate. Okay, so they literally go in, well, out, and in, and just change their radius regularly with time. And because they're changing their radius, then the luminosity is going to change, but also more importantly, their temperature changes. As they expand, the surface layers get cooler. As they contract, the surface layers get hotter, just due to thermodynamics. And so that's why they change in brightness. So, and this is, they have a regular period, okay? So they will, you look at their light curve, the brightness is a function of time. It goes up and down in a very regular fashion with a regular period. So here's an example of that. Let's maybe start at the bottom right here. So this is what you actually observe. So this is the apparent magnitude as a function of time for one of these cepheid variable stars. In fact, this might be delta Cephei, the original one. You can see it's a naked eye star. When I was an undergraduate, we were, for a little project, we were sent out every night on the roof of the hall residence to go and with the naked eye try and estimate how bright the star was each day, and then plot the curve and and work out how far away it was. So you can see that the changes by about a magnitude here, so it's quite a significant change in brightness. So again, easy to spot, and they have these kind of characteristic sawtooth type light curves. And you can see they're quite a convenient sort of period, usually a few days or a few weeks. And the reason for their changes, so as I said here, so this is the diameter of the star changing with time. Okay, so you can see it's changing by sort of 15% or so over the period. Okay, and those changes in the size also cause changes in the temperature. Okay, as you can see in this curve. Okay, so again, it's changing by about 1,000 Kelvin, so it's quite significant. And you can see that actually the light magnitude change is really driven by the temperature change rather than the size. And don't forget there's a 2 to the 4 dependence on the temperature and the luminosity. Okay, so that's what a cepheid variable light curve looks like. So all well and good, but how does that help us? Well, it helps us because of this. Okay. So there is an extremely good correlation between the period of the pulsation, so how long it takes for the star to go up and down in brightness, with the actual intrinsic luminosity of the cepheid variable itself. Okay. So this is referred to as the period luminosity relation. There is a bit of a complication because, as we shall see in a moment, then the exact period depends also a little bit on the metallicity, well, quite a bit on the metallicity of your star. So that's, again, metallicity is the amount of heavy elements in your star. So it depends a little bit on the composition of the star. So basically it depends whether it's a population 1 star, metal rich, or a population 2 star, metal poor. But once, if you've got some idea on which of these it is, then you're okay. And here's an illustration of that relationship. So this is the period luminosity relationship for cepheid variables. So, and it's split into these 2 types, which refer to, these are the population 1 ones, and these are the population 2. So if we just look at the population 1 ones, you can see that, you know, this is the kind of relationship. So that there's a strong correlation between the period. You can see here it varies between sort of 1 and 100 days here, and the luminosity. Okay. And of course, it's this quantity, the luminosity, the intrinsic brightness of the star, that we want to know in order to be able to find the distance to one of these objects. And so basically all we need to do is observe our cepheid variable for long enough that we can determine its period. Okay. We'd then want to work out whether it's a type 1 or a type 2, so whether it's in population 1 or population 2. You can often do that perhaps by looking at its location and what type of galaxy it's in. Okay, so if your cepheid variable is located in the spiral arm of a spiral galaxy, then it's more than likely to be a population 1 object. Okay. If it's located in a halo or located in an elliptical galaxy, it's much more likely to be a population 2 cepheid. Okay. So that's one way of doing it. Okay, so once you know which one it is, you can then just read off its luminosity or absolute magnitude and work out its distance. Yeah, so this is the method, all right? So you measure the period and you can determine the absolute visual magnitude. You can see the periods are quite easy. You don't have to wait years for them to vary. And a real breakthrough in this came again, yet another, so pretty much one of the main science cases actually for the original Hubble Space Telescope was to be able to detect and monitor cepheid variables out to significant distances from us. So like the Virgo cluster was a key target of galaxies, to measure the distances to with the cepheid experiment, which we'll see in the next lecture that this was sort of a key breakthrough in determining the famous Hubble constant. And here's an illustration of that. Okay, so this is one of those galaxies, M100, that's in the Virgo cluster. And way out in the outskirts of this galaxy, you can spot variable stars. So this is the idea that of them being easily identifiable, because you just need to take a sequence of images of your galaxy and look for stars that are varying by a magnitude or so, and then follow them for a significant few periods so that you can characterize the shape of that light curve to check that it really is a cepheid variable, and then do the process of looking at the period, etc. And for those of you on the physics or astrophysics degree program, then you can do this experiment for yourself in the second year lab by looking at the cepheid variables that the Hubble Space Telescope studied. Okay, so in the spirit of doing things yourself, so here's a little example. Okay, so imagine you found a cepheid variable in another galaxy with a period of 15 days. Okay, and its average apparent magnitude is 27.8. That's what's plotted on this graph. Obviously, so again, it is slightly counterintuitive because this is a variable star and we're trying to accurately find its magnitude. But the way you do that is you just average over the light curve to find the average apparent magnitude, and that's what's plotted. Well, in fact, this is the average absolute magnitude, again, for one of these variables. But okay, so use the graph below, just estimate by eye, and use the information here to work out how far away this one is. Assume it's on this line, the type 1 cepheids, and ignore any extinction. But normally the colors of cepheid variables are also, the intrinsic colors are very well understood from studying ones in our own galaxy. And again, I think there's a relationship there with period as well. So we know their intrinsic colors very well. So again, as we learned in the lecture on interstellar dust, if you know the intrinsic color, you can measure the observed color, and that will allow you to work out the extinction quite easily as well. So you can correct for extinction if you need to. But here, just ignore that, just to see how this works in practice. Okay, so have a go at that, and we'll come back after the break.